So the goal of this lecture is to understand when is it that GG transpose is actually the optimal solution to this problem, where B is the signed adjacency of the random graph given by the stochastic law. Okay? So how does one prove that something, right, that X equals GG transpose is the optimal solution to a problem like this? Right, so how do you prove that something is the optimal solution to a problem? One thing you can try to do is look at optimality conditions, in particular local optimality conditions. Right, if you have a problem and you have a point, the conditions for it to be a local optimum, if there are no constraints, right, it basically needs to have gradient 0 and the Hessian needs to point out. So when there are constraints, this gets a bit more sophisticated, and this is known as the KKT conditions. Right? But this could be one way. Of course, if your problem is non-convex, then just looking locally might not be enough, right? It could be that this goes up and then goes down more, right? So that maybe is not enough. However, this problem is convex, right? This is linear, and this is a convex constraint, right? But the approach we're going to take, which is essentially the same as this one, is the approach of duality. So for every problem of this style, there is a dual problem. This will be another optimization problem that we know it's always above this one, right? The picture of duality is that here we're trying to maximize something, primal. And it's going to be another problem that's going to try to minimize something, the dual. And we know for sure that it's always above the other one. Which means that if we want to prove that something, say GG transpose, is an optimal solution for the primal problem, any feasible solution of the dual problem will give us an upper bound on any possible feasible solution of the primal problem. So if we can find a feasible solution for the dual that matches the value of this one that we want to prove, it immediately proves that nothing can beat it. Right? If we find something that matches the same value, then we know that nothing else can beat it. We still need to prove that it's the only thing, right? That there's no other solutions. Because if there's like 5 solutions to this, we have no guarantee of getting GG transpose, right? You could potentially get a different one. We want to make sure that we can recover GG transpose, right? The optimization problem is only here because it's something we can solve and the solution has statistical meaning, right? It's learning meaning. And so we're going to make sure that it's the only solution so that we don't get some spurious one. Okay. So what I'll do in this part of the lecture is I'll describe duality in sort of a somewhat different way. Right? There's many ways of describing duality. What I'll do here is I'll describe duality via a game, sort of a primal dual player game, right? A game with 2 players. And the idea will be, as you've seen a few times already in this course, to take the constraints and put them in the objectives. So we want to take away the constraints. So we're going to write this, right? Let's call this the primal problem, right? This is our STP. Right, we're going to take it, I'm going to write it in the following way. We'll take max of x, right, of the trace of xp. But now we don't want to add the constraints. We want to enforce the constraints in another way. And we're going to do so by having the dual player. So there's going to be another player, right? We can think of this as a primal player, and this as a dual player. The dual player goal is to minimize this, what's going to show up here. The primal player's goal is to maximize. And so what the dual player will do, in the way that we construct this, is that the dual player will have ways of exploiting the fact that the primal player does not satisfy the constraints. Okay, so I'm going to write this down, and then I think it will be easier to see. Trace over. Just make sure I have exactly the same thing as the notes. Okay, and now I'm going to write it in. Okay, so let's see why the constraints are sort of being enforced in an indirect way. So if for some reason the primal player, right, the primal player wants to maximize this, sure. But let's say the primal player ends up giving a solution for which xii is not 1. If xii is not 1, then this means that there is a diagonal element here, right? The entry I of this is not 0, right? 1 minus xii would not be 0. If that's not the case, then we can take just zii, right? Zii can be just, for example, minus c over this, right? Since we're not dividing by 0, this is okay, which would mean that the term that would show up here, this term, the entry ii of this, would be equal to c, right? The term I of this sum, like term I, would be equal to a constant c, or minus c, actually. Right? And we can make c as big as we want, which means that we could drag the dual player, the primal player plays x. If x does not satisfy this constraint of xii being 1, then the dual player can pick z, such that zii is, for example, this, the rest can all be 0, and gets a value here, right? And let's say the rest of z, zijj, is 0 for all j different than I, then the value of this is just minus c, and I can just make a c as big as possible. So this means effectively the dual player is able to drive this value all the way to minus infinity, right? So terrible news for the primal player. Therefore, the primal player will try always to satisfy this constraint, right? The same thing happens here. Let's say that the dual player does not satisfy this. Then this means that there exists some vector v such that v transpose xv is equal to is negative. So say it's equal to minus lambda for lambda some positive constant. Right? But then again, Q could just play C times V transpose V for some constant C. Right? What would then this look like? Right? This would look like the trace of C V transpose V, V transpose. What it would look like, well, the C is a constant comes outside, the V goes to the other side, so it would just look like C V transpose X V, but this is just minus lambda C. Right, since lambda is positive, and I can take C shooting to plus infinity, I can also drive this to minus infinity. So what I showed here is that it is in the interest, of course, of the primal player to play exactly under these constraints. Right? And then if they play within these constraints, then what can the dual player do? Right? The dual player, if they play with these constraints, then the dual player cannot affect this term. Here, this is for sure positive, right? Because x is positive semi-definite and q is positive semi-definite. And here, x minus identity will be zeros in the diagonal. Since z is diagonal, this is also 0. Right? So the dual player can only make these things potentially negative, potentially positive, potentially more positive, which means that this for sure is bigger or equal than the value of the primal. Right? Because if x plays the optimal solution of this, right, then they can get at least p. But I argue that the dual player can make them get exactly p. Right? Because all the dual player needs to do is the dual player needs to play q equals 0, right? And z equals 0, and they get exactly, these terms are exactly 0, so this is smaller or equal than p. Okay? So this means that this is exactly the same as the primal. Okay, so we saw that the value of this is exactly p. Right? Because the dual player effectively is forcing x to play exactly those constraints. Right? So x needs to play on those constraints, otherwise it's goes to minus infinity. And then if x plays on those constraints, the dual player can just play 0 to get exactly the same value. If the dual player decides to play something else, will only get bigger, and it doesn't have an interest in that because it wants to minimize. Right? So this is exactly the same as the primal. Okay? Now I'm going to change the rules of the game a little bit. Okay? Now I'm going to swap the order at which these players play. Okay, I'm going to let the dual player play first. And the primal player is going to play afterwards. And now the question is, who is in a better position now? Right? Now that I swapped the order of the plays, right? It's exactly the same thing. I just, before the primal player was playing first, the dual player was playing after. Right? Now, the dual player gets to play first and the primal player plays after. So what is best in this game? Is it to play first or second? Right? So maybe take a second to think about this. Right? So in this game, I claim it's best to play second. Because right, it's not about playing first or second, because nothing here depends on playing first or second. But it's about whether a player gets to see the play of the other player before making their decision. Right? In this case, the dual could adapt to what X did. And in fact, that was the strategy to drive this to minus infinity. Here, however, the dual player needs to decide Q and Z before they see what the primal player played. Well, the primal player gets to pick X only after they see that the dual player played Q and Z. Right? So for sure this is bigger or equal than P. Okay, but now, okay, so this is bigger than that. Now let's try to rewrite this. Exactly how the trick we did here, right? Let's try to understand better what is the best play that the primal player can do given Q and Z, so let's group the terms on X. Okay, so we have that P smaller or equal than, let's rewrite this, minimum Q bigger than 0, Z diagonal. And then what we have max on X of trace. And now what are the terms with X? We have B plus Q minus Z, right? X plus one term that doesn't have X, which is trace of Z times identity, is just the same as trace of Z. Okay, but now when we look at this, it's clear what the dual player needs to do. Because if the dual player plays something here that's not 0, then the primal player can just play, right? There's absolutely no constraints, right? So they can just play that matrix. Right? You can just play that matrix times the constant C and get basically C times the trace of the square of the matrix. And because the matrix is symmetric, right, the trace of the square will for sure be positive, right? It's a Frobenius norm, unless it's 0. And so the primal player could drive this up to infinity. Right? So it's clear that the dual player, right, dual player is forced to play B plus Q minus Z to be 0. Has no other option. And so we can actually define Q as equal to, right, Z minus B. Right? There's absolutely no other option. And so we can think of what the primal player is doing, right? Really what the primal player is doing. Let's see if I write here. Okay, so what we have that P is smaller or equal. Then what is the dual player doing? Just playing the minimum, right? There's really one thing they can decide, which is Z, right? Q becomes decided immediately. So Z needs to be a diagonal matrix, right? What is the constraint is that Z minus B needs to be positive semi-definite. So Z minus B needs to be positive semi-definite. And what they're trying to minimize is the trace of Z. Right? And this is what we call the dual program. Right? This is the definition of the dual program. Okay. Okay, so this now is the dual program, and what we prove is that the value of the dual program is always bigger than the value of the primal program. Right? So now let's write that. So we can call this the primal, take away this picture. Okay, so what is the dual? The dual is minimize trace of Z such that Z is diagonal and Z minus, sorry. Okay, so what we know is that the dual problem is always bigger or equal than the primal. And although actually proving this is a lot easier than what we did, okay, let me do you the proof. Let me give you a proof of this. And so this is known as weak duality, proof of weak duality. But I believe it's not as enlightening, right? Because this sort of game that you can build can work out the dual of anything, or mostly anything. While this proof, I mean, proves that the value of this is bigger than that, but it doesn't, it's not so easy to derive the dual that. Okay, but so what you do is the following, right? So you take this value is positive, this matrix positive semi-definite, that matrix positive semi-definite. It's not hard to see that the product of two positive semi-definite matrices is always positive. Right? So if indeed X is feasible here, this is positive semi-definite. If Z is feasible here, this is positive semi-definite, therefore this is bigger than 0. And now if we work this out, what do we get? Well, we get trace of X times Z, but since Z is diagonal, it only picks up the diagonal terms. X has only one in the diagonal, so this is just trace of Z, minus trace of XB. Trace of BX, right, it's the same. Right, so since this is bigger than 0, it shows that, right, this is bigger than that, and, oh, the other way around, sorry, that this is bigger than that, and it shows what we want. Right? So this means in particular that if we find, right, if we find some let's call it Z natural, such that, right, Z natural is dual feasible, right? All this means is that it satisfies these constraints. And trace of Z natural is equal to the value of that when we place GG transpose B. Then it's a proof that no value can beat GG transpose, right? Because if, when I compare this to GG transpose, right? When I plug in the Z natural, I get the value that I get here for GG transpose. Right? This means that I have effectively, let me look at it, right? Since this is GG transpose, I have effectively found a point that proves that nothing can beat this. Right? Gives an upper bound that GG transpose is at least an optimal solution. But there's now two questions, right? One is, why would such a thing exist? Right? Even if GG transpose is optimal, here I'm just saying this is upper bound. Why should it be an upper bound that actually matches in any interesting situation? And two, how do I find such a thing? Right? 3, how do I prove then that GG transpose is actually optimal? Right? And that we can't actually have any other one. Right? And so the fact that this upper bound should exist is given by strong duality. Strong duality says that in many circumstances, I mean, it's a bit outside of the proof of this course to talk a lot about strong duality, but strong duality says that in many instances, the value of the primal is actually equal to the value of the dual. So if GG transpose is optimal, in this case, does satisfy those constraints. So if GG transpose is optimal, then there is a proof of it. Right? So there is Z to look for. Okay. So how do we look for Z? Okay, so we do the following. So we know that if indeed Z natural is to be an optimal solution here, and GG transpose 1 here, it must be that when I replace, right, so if Z natural is optimal, right, because if it matches, then it also itself needs to be optimal. And X is optimal, then we know that this needs to be 0, right? And GG transpose is also optimal. It must be that, right, it must be that though these two values are the same, so it must be that this trace is 0. So it must be that a trace of GG transpose times Z minus B, right, this needs to be 0. Right? This is actually known as complementary slackness. So this is known as complementary slackness. So what we have to look for is Z natural that satisfies this. Okay. So there's still a lot to look for because we only have one constraint, and Z natural is n nodes, right? The diagonal is always known. But actually, right, see about what we have here, right? We know, look at this, we know that Z natural minus B is positive semi-definite. And we know that G transpose Z natural B minus B, G is 0, right? Because that's what that constraint tells us. This means, right, this together implies that actually this needs to be 0 even before I hit G transpose on the other side, right? G actually needs to be the kernel. G needs to be on the kernel of Z natural minus B, right? Because if we have a positive semi-definite matrix and G transpose times Z times G is 0 means it's an eigenvector with eigenvalue. What we need to look is we need to look for Z naturals that satisfies this. This gives us n constraints, right? So we need to look, so the goal is we need to look, okay, let me not write the goal for now. We need to look for Z natural, diagonal, right? It needs to be diagonal. Needs to satisfy that Z natural minus B, G is 0. Right? And notice how this is n constraints. This is n constraints and right here we have n constraints, but n variables. Right? So this is n variables and n constraints. Right? Because this is diagonals n variables, and here we have n constraints. Right? And of course, we need it to be feasible. So we need Z natural minus B to be positive semi-definite. Right? But now, how do we make sure that there's absolutely no other solution that could also be optimal here? The key lies in complementary slackness. We know that if there was to be any other solution, right? If there was to be any other solution X, then it would have to satisfy that the trace of X, Z natural minus B, need to be 0. But since this is positive semi-definite, and this is positive semi-definite, there are no cancellations in this. So if I write the spectral decomposition of X, right, all those vectors, say VI transpose, they need to satisfy that VI transpose times this times VI is 0. So the entire image or column space of X needs to be in the kernel of this matrix. So if I make sure that this matrix doesn't have anything else in the kernel besides G, then X can only have in its column space G. So it needs to be a multiple of GG transpose. But since we know that the diagonal entries are equal to 1 because of this constraint, then for sure, the only thing X can be is GG transpose. It cannot be any other multiple, right? Look at the 1-1 entry. The 1-1 entry of GG transpose is 1. And X needs to be 1 there, so it cannot take any other multiple. So all we need to ask is for another constraint. We need to ask that lambda 2, right, the second smallest eigenvalue of Z minus B is strictly bigger than 0. Right? And so essentially what I just did is I proved that if this is satisfied, right, if such a Z natural exists, so if Z natural exists such that this, then GG transpose is the optimal solution. It's the only optimal solution of the problem P, of the primal problem, right? So we know that now we've reduced it to understanding the existence of this matrix X. Now because, Z natural has n variables and n constraints, we can just solve the linear systems. Right? So we can solve this linear system, will tell us what Z natural needs to be. Right? It's actually quite easy to write. We'll see it in the next lecture. Right? But we have that it's diagonal. This gives us n variables and constraints, so we can just write it. And so there's really, unless there's some degeneracy here, which there won't be, there's really only one possibility for Z natural with these two constraints. And all we need to do is to check that the other constraints are satisfied. So of course, Z natural will depend on B. So the solution of this will be a random matrix. And the question we have to ask ourselves, does that random matrix satisfy this? Right? So we reduce it to a question in random matrices for which we're going to use matrix concentration. Okay, so in the next lecture, we're going to derive those equations, look at Z natural, and then use matrix concentration to prove that in certain regimes it does satisfy this. Okay? Now what is called, like Z natural is often called a dual certificate. or a dual witness. Right, so because it's certifying that GT transpose optimal solution, or it's a witness to the fact that GT transpose optimal solution. Okay, so next lecture what we'll see is how to build Z-natural, so on these two constraints, and how to use matrix concentration random matrix theory to prove that that Z-natural will actually satisfy this for certain ranges of P and Q. Okay, thank you.